Okay, so if you did not have any problems until now, let's look at how we can prove identities then we can do some problems that involve proving identities. If there are no questions apart from that. Okay, so that's all right. Let's quickly revise what we have done until now. Not revise, I'll just list down the concepts that we've done until now. We talked about ASTC, how different functions are positive and negative in different quadrants. We talked about the basic angle. Then we use those two things to basically solve equations, right? We learned how to solve equations with angles in degrees and in angles in radians, with different kinds of intervals given in the questions. Okay, so that's what we did. We learned how to solve equations. And then in the last session, we also looked at these identities that we have. One is sine square theta plus cos square theta. That is identical to 1. That's one identity that we've got. And then there's another one, tan theta is identical to sine theta over cos theta. And by rearranging them, we get a couple of other forms as well. That's what we looked at. And then we looked at one example from the worksheet as well, in which we had to solve an equation in which we had two functions, sine and cos. So what we did was we first used the sine square plus cos square equals 1 identity to convert sine square to 1 minus cos square. And then it became a quadratic equation. We solved that quadratic equation to find the possible values of theta from that. That's what we've done until now. I asked you to do questions from the worksheet after this as well. Now, today then, we will focus on how we can prove identities. But before that, I think there's just one question that I want to do quickly, and then we can start with proving identities. So let's have a look at question number 1, for instance. Okay, the very first question. Let's have a look at this. How we can solve this question. Okay, it's a short one. Then we'll discuss proving identities after that. Question number 1 from the worksheet. So it says, show that the equation sine square theta plus 3 sine theta cos theta equals cos square theta equals 4 cos square theta can be written as a quadratic equation in tan theta. How many of you have done this question? Who has done this question already? No one yet? Okay, so let's try this now. Aima has done this, okay. So how do we approach this? First of all, anyone apart from Aima, then we'll ask Aima if nobody answers. Yes. Any idea? How do we want to write this in terms of tan? Sine square theta plus 3 sine theta into cos theta equals 4 cos square theta. Now, when you're doing these questions, you're going to have the identities in front. What are the identities that you have in paper 1? Sine square theta plus cos square theta. That is identical to 1. And tan theta is identical to sine theta over cos theta. These are the two identities that you're given in the formula sheet. Now, what we want to do is we want to convert this equation to a form that only has tan theta. Now, for tan, we only have one identity, and that is sine over cos. How do we use that identity here to convert everything to tan? Yeah, so that's a very good idea. Yeah.
Yes,
Yes,
sir, we
Abdullah?
can take 4 cos square theta to left side and divide all of the equation by cos square theta, cos theta.
By
Multiplying,
cos
basically
theta?
multiplying.
Multiply?
No, I,
If
I
you
mean divide, sorry.
divide. Uh, check if that works. So I is saying, okay. So the idea behind that is that for tan, we want cos in the denominator, right? So if we divide the whole equation by cos, what does that give you? You have sine theta. This is sine square theta. So one power can be separated, and the rest sine over cos can be written as tan theta. And here you have 3 sine theta. And on the right side, you have 4 cos theta. Yes, you have a tan from that, but not everything is converted to tan using this. We still have a sine here. We still have a cos. We have another sine here. We have a cos here. So dividing by cos only is not going to be enough. Or what you can do is you can divide by cos first and see if that helps. In this case, you have one tan, yes, but the rest of it is not converted to tan yet. So now you can divide by cos again. If you reach this point, you can divide by cos again. And this sine over cos, that gives you tan as well, and that gives you tan square theta plus 3 tan theta equals 4. That could be one idea that you can do it step by step. If you divide by cos and you figure out, okay, that's not enough, you can divide by cos again. Or, as you're now saying, the direct way of doing this could be, since we want to convert everything to tan, we have sine square here. If we want to convert sine square to tan, remember what we talked about when we discussed identities? If tan theta is identical to sine theta over cos theta, then what about tan square theta? Tan square theta is identical to sine square theta over cos square theta. So if you were to divide the whole equation by cos squared instead, so you could think of it like this, that you divide each term by cos square, like this. Or you could think of it like this, that you take this cos square to the other side and divide. It's the same thing. You get the same result for both, but the idea is that you divide by cos square. When you divide by cos square, what happens is sine square over cos square, what does that become? That becomes tan square theta. And then here, one power of cos in the denominator gets cancelled with the cos in the numerator. And what you're left with is 3 sine theta over cos theta. Let me write that here first. On the right side, cos square theta and cos square theta get cancelled, and we just have 4 left. So now we have tan square theta plus 3 tan theta, sine over cos is again tan, minus 4 equals 0. And this is the quadratic equation that we have now. Okay, that's what we wanted to do in the first part. We had to write this as a quadratic equation in tan theta, and that's part 1 done. Okay, now let's look at part 2. Part 2 says, hence or otherwise solve the equation in part 1 for theta between 0 and 180. So now you have to use what you have done in the previous part to solve this equation. Now you've already converted that equation to a form that only has tan. So what you can do is you can solve this equation now. You can use substitution. You can say let u equals tan theta, or any other letter for that matter. It doesn't matter. U squared plus 3u minus 4 equals 0. You can factorize this. It becomes u squared plus 4u minus 4 equals 0. You get two factors from that, u minus 1 into u plus 4. That means either u equals 1 or u equals minus 4. Now you put that substitution back, and that gives you either tan theta equals 1 or tan theta equals minus 4. Now you find the basic angle just like you usually do. Tan alpha equals 1. The interval that's given to you in the question is that theta is between 0 and 180. That's the interval given. And now you can find the basic angles. The basic angle from the first one would be 45 degrees. Since tan is positive in the first quadrant and in the third quadrant. So it could be first or third. However, since the interval is from 0 to 180, the third quadrant is not possible. That's outside the interval. This is the only possibility from the first equation, 45. So one possible value of theta, therefore, is 45 degrees. Find the basic angle from the second equation. What does that turn out to be? Basic angle from the second equation, what's that?
75.963.
75.96. Thank you. That's the basic angle. Now, since tan is negative here, we could be in the second quadrant or in the fourth quadrant. But again, fourth quadrant is not in the interval, so we have to ignore that. So the only possible answer that we're getting from this is this here. So theta equals 180 minus 75.96, which turns out to be 104.0 degrees. So theta is either equal to 45 or it's equal to 104. Make sense? Any issues with this?
No, sir.
Okay, so this was one good one, which basically tells you that you can sometimes divide by cos square like this as well. Okay, and that helps with your solution. Okay, now let's have a look at how we can
Sir, we
paper
cannot
3
hear
as well.
you. Sir,
Can't hear me?
your voice gets muted when you speak in between.
No one can hear me? Is that the same for
Sir, we can
everyone?
hear you. Sir, we can hear you now.
Okay, was it breaking for everyone before?
Yes, sir.
Yes, sir.
Okay. I'm not sure what the problem is. Maybe this got connected to. Okay, maybe it was just a one-off. All right. So now we want to understand how to prove identities. Okay, that's the next thing that we want to do. Now, this is going to be a major part of trigonometry, not just in paper 1. You'll find later in paper 3 in your A2 that you have to prove a lot of different kinds of identities. So you need a lot of practice on this as well. But in paper 1, you only have 2 identities that you've done until now. So this is not going to be as complicated as it would be in paper 3 later, because you'll have a lot of different identities there. If you look at the formula sheet, there are like 15, 16 new identities in paper 3 that you'll be doing later. But for now, it's not that difficult because we only have 2 identities. And you have to use these 2 identities to prove some other identities. Now, let's start with this. Proving identities. So what we've done before is we have talked about these 2 identities that you need to know of. They are given in the formula sheet. You can just believe them to be true. You don't have to prove them, although we discussed how we can prove them as well. where they are going to be given in the formula sheet, you can use them directly. All right. But now using these two identities, you will be asked to prove some other identities. So for example, this is where they ask you to prove this identity. 1 minus tan square x divided by 1 plus tan square x, that's identical to 1 minus 2 sine square x. You have to prove this identity. What does that mean? You have to prove that the left hand side and the right hand side actually the same thing. They're just two different forms of writing the same thing. Just like 2 into x plus 4 is identical to 2 into x plus 2. These are two different forms of writing the same thing. You have to prove that these two are two different ways of writing the same thing. So you have to start from one of these two sides, mostly the left-hand side. Sometimes, in rare cases, the right-hand side as well. We'll discuss how to choose that, how to decide that. But generally, what you have to do is you have to start from the left-hand side and convert that. It becomes the same as the right-hand side. So you have to change that to a form that it becomes this. Okay. Now let's go through this process once, and then we'll discuss some tips that you need to keep in mind when you are proving identities. But let's start with this example first of all. This is the left-hand side, and this is the right-hand side. Start from, let's say, the left-hand side and prove that this can be converted to this side. Okay, that's the idea. We start from this side, 1 minus tan square x divided by 1 plus tan square x. And we want to change it to a form such that it becomes this. And how do we do that? We do that using these two identities that we already know are true. Sine square theta plus cos square theta is identical to 1, and tan theta is identical to sine theta over cos theta. Okay. Now we will be discussing a method that you use for this generally, and that is that you basically look at what you have at the moment and how you can convert it to this form. But you'll find that every single question like this is going to be different in the sense that you'll have to figure out at that very point how to go from this starting point to this end point. So basically, it's like solving a puzzle in a way that this is the starting point and this is the end point. You have to go from this starting point to this end point, and these are the paths that you can take, right? Sine square plus cos square theta is identical to 1. That's one path that you can take. Tan theta is identical to sine theta over cos theta. That's one other path that you can take. They have multiple paths available. And using those paths, you have to go from this starting point to this end point. That's the idea. So it's like solving a puzzle like this. And like all puzzles, you get better at it with practice. So it requires a lot of practice because once you've done that, then you kind of get better at it and in understanding how to go from one form to another. So that's very important that you do a lot of practice in this. So as I said, it's like solving a puzzle. And these are the paths that you can follow. And like in puzzles, when you have to go from one starting point to the end to an end point, a lot of times what happens is some paths are more efficient and some paths are maybe longer and not that efficient. That also is something that you will learn with practice, that there are always going to be multiple ways of proving identities. You could prove it one way or another way or another way, but one of them might be doable in 3-4 steps. Another method might work with 9-10 steps. Another might take 20 steps. So depending on what you choose to do, it can end up taking less time or more time. Okay. And how do you decide, how do you figure out which method or which steps are going to make this process quicker? Again, we will be learning some tips along the way. And you'll be practicing like at least 15-20 questions on this, on proving identities, and that will make you more efficient at going from the starting point to this end point. Okay, now let's go through this process once using this particular question. So it says 1 minus tan square x divided by 1 plus tan square x. This is identical to 1 minus 2 sine square x. So we have to start from this and end at this. We have tan in this original form. Which identity has tan? It's the second identity. And what we want to get to is something that has sine only. So we can start like this, that we can say, okay, let's convert tan to sine over cos. That's one starting point that we can have here. Let's change tan to sine over cos. Okay, so it's tan square, so it's going to become sine squared over cos squared. So you get sine squared x over cos squared x like this. And then in the denominator, you have 1 plus sine square x over cos square x. So you convert everything to sine and cos like this, using this identity. Tan theta is identical to sine theta over cos theta. What do we do now? We can simplify this. So it's not always going to be very clear what you should be doing to go from this to this. You will start doing it by using one of the identities, and then after doing a few steps you'll realize, okay, whether this is going in the right direction, or maybe you need to change your direction again. That happens in puzzles as well, that you follow one path and then you realize, okay, this is a closed end, or maybe this is not very efficient. Then you can take a step back and do something else. So that's how it works. Okay, so sometimes you end up doing something and you get stuck and you can't figure out what to do. So what you have to do at that point is you have to take a few steps back and maybe take another path from there. So all of these things are going to be relevant when we do this. Okay, so now in this case, what we did was we converted tan to sine over cos. What do we do now? We can take LCM. We can take LCM in the numerator and in the denominator. How do we do that? This is going to become cos squared minus sine squared x divided by cos squared x in the numerator. And in the denominator, we have cos squared x plus sine squared x divided by cos squared x. Okay. And now, since the denominator is the same, we can just cancel them out, right? It's just like, you can write it like this to understand this better. If you get confused by fractions like these, you can say this is cos square x minus sine square x divided by cos square x divided by cos square x plus sine square x divided by cos square x. Now this is the division sign. If you convert it to a multiplication sign, what would this become? Cos square x minus sine square x divided by cos square x multiplied by cos square x divided by cos square x plus sine square x. So that's why we can just cancel these cos square x out like this. Okay, so this and this, they get cancelled. Okay. Now, what are we left with? We're left with cos squared x minus sine squared x divided by cos squared x plus sine squared x. Now, what's this? What's cos squared x plus sine squared x?
1.
This is 1, right? Sine squared x plus cos squared x, or cos squared x plus sine squared x, that's 1. So in the denominator, we have 1. What about the numerator? In the numerator, we've got cos square x minus sine square x. Now, keep the end in mind. What do you want at the end? You want 1 minus 2 sine square x. So in the final result, you only want sine and no cos. So you have cos square here. What you can do is you can change cos square to 1 minus sine square. So it becomes 1 minus sine square. Instead of cos, we have input this, and we have minus sine square, this one as it is, and that gives us 1 minus 2 sine squared x, and that's equal to the right hand side, and that is what we wanted. we have proved this identity that the left-hand side here can be converted to this form. So that's why they are both supposed to be identical. They're both exactly the same as each other. Is that all right?
Sir?
Yeah.
Sir, in the first step, can't we cancel cos square x and cos square x when you converted tan square to sine square over cos square?
No, we can't do that here because we also have this one added here, no? We can't do it without taking LCM. It's not. You can think of it like there's a bracket here like this, right? You first have to evaluate those brackets, and then you can do anything else. Okay, so you first have to simplify this. Without taking LCM, you can't do that cancellation. Is that okay?
Yes, sir.
Any other questions on this?
No, sir.
No? Okay, now you will actually often come across fractions like these. So you need to be very sure that you know how to deal with a fraction in the numerator and a fraction in the denominator. So let me explain this to you on the side here, because that's simple algebra, but you can't afford doing any errors, algebraic errors in fractions like these. A lot of people end up doing errors here. Over B over C over D. If you have something like this can be written as A into D divided by B into C. Okay, how does that work? A over B over C over D, the same thing as A divided by B, A over B divided by C over D. Converted to multiplication form, that becomes A over B into D over C. And that's where we get this from, AD over BC. Okay. This is how I kind of remember this. This is how I do this quickly, that the denominators are going to switch places. So the denominator below above, the denominator above goes below, gets multiplied in the denominator. So denominator is basically switch places. D is going to go above and B is going to go down. Numerators stay where they are, denominators switch places. So D goes above and B goes down. That's where we get this from. If you have, for instance, A over B whole divided by C, if you have something like this, the denominator goes down. So it becomes A over BC. And similarly, if you have A over B over C, if you have something like this, denominator goes up and it becomes AC over B. Okay, so that's how you deal with multiple fractions, a fraction above and a fraction below. The denominators basically switch places. They get multiplied above or multiplied down. Make sense?
Yes, sir.
Okay. All right, so now this was one example in proving identities. You have to use these two identities to prove some other identities. Now, there are some thumb rules that you need to keep in mind while proving identities. Let me just write them down. We'll understand them one by one. So number one, how do you choose which side to start from? Generally, as I said, you will be starting from the left side. Mostly they give identities in a form that starting from the left-hand side is going to be easier. So mostly you'll be starting from the left-hand side, but that's not always the case. Sometimes starting from the right-hand side is more efficient. The idea is you start from the more complex side. Start from the more complex side. Okay, that's the idea. Start from the relatively more complex side. Now, how do you decide which side is more complex? That's the question, right? How do you decide which side is more complex? Now, if we look at this, you have a fraction on the left side. On the right side, you do not have a fraction. It's much easier to simplify a fraction to make it something like this, rather than going the other way around. It's going to be much more difficult to convert this to a fraction. Okay, simplifying a fraction and getting rid of the fraction is easier as compared to converting something like this to a fraction. So going from right to left here would be more complicated. So you start from the more complex side and simplify that. That's the general rule. Okay. Now, how do you decide which side is more complex, right? How do you decide complexity, basically? There are different thumb rules that you can keep in mind for that. One rule is a side is more complex if, let me write that here. It's more complex there are different types of functions. Different types of functions. A side is more complex if there are different types of functions. What does that mean? If one side has both sine and cos, and the other side only has sine, then the side that has different functions, sine and cos, that is more complex as compared to the side that only has sine. So it'll be easier to go from this side to the other side. Okay, the side that has more different types of functions. Okay, that's the first thing. Then another thing that you can look at is that we did in this identity as well. In this case, we had one function on each side. We had tan on one side, sine on one side. So there were no different types of functions. So another thing that you look at is it's more complex if there is a fraction. So if one side has a fraction and the other side does not have a fraction, then it's mostly easier to start from the side that has a fraction, okay, rather than the other way around. And if none of them can be used to differentiate between the two sides, another idea is a side is more complex if there are more number of terms. For instance, on one side, if you have one thing being added to another thing and subtracted to another thing, and on the other side, you just have one term. Now, keeping in mind everything else constant, this side has 3 terms, this side has 1 term. It's going to be much easier to go from this side to this side, as compared to the other way around. Okay, so that's how we can decide whether a side is complex or not. Okay, these are just thumb rules. Now they sometimes may be broken as well. You can find some example made in which going the other way around might be more efficient, but 99% of the times, this is what is going to be more efficient if you look at these rules. Okay.
Sir,
Yeah.
sir, what about if we go from a square term to a non-square term?
Yeah, so that also works. So if one side has something like this, if you have a square here and the other side does not have a square, yes, simplifying the square be easier as compared to making this a perfect square. Yes, that's also a good rule that you keep in mind, right? So these are just common rules that you can keep in mind. And yes, and apart from that, you can, kind of decide yourself, okay, which looks more complex to you. So in this case, for instance, if you have a square like this, yes, that makes sense. This would be more complex. It would be much easier going from a square to this form in which we don't have a square as compared to the other way around. So yeah, that's a good point. Okay. So now using this, you decide which side to start from. Then the idea is, if the left hand side is more complex, you start from the left hand side and make it equal to the right hand side. If the right hand side is more complex, you start from the right hand side and make that equal to the left hand side. Okay. There's another possibility as well. And that is that sometimes what happens is both the sides are it can happen here as well sometimes, that both sides are quite complicated. Okay, so you're kind of confused, okay, which side to start from. Both are very complex. Another idea that you can use is you can simplify both sides. Start simplifying both sides. Since both are complex, that means you can simplify both a bit. Simplify both sides. And then at some point, you might be able to make them equal after simplification. So you simplify both sides and meet somewhere in the middle. That's another possibility. That's another way of proving identities as well. You don't necessarily have to start from one and then prove that equal to the given form. You can simplify both forms. And then if at some point you get the same thing here and the same thing here, then that means they are supposed to be identical. Okay, meet somewhere in the middle after simplifying both sides. So you can use any of these three methods for proving identities. Okay, now while you're doing this, keep one thing in mind. Do not take terms from one side to the other while proving identities. You can't do that. Okay, you can't take terms from one side to the other while you are proving identities. For instance, if you were proving this identity, if you had to prove this, let's assume if you had to prove this identity, then you can't say sine square theta is identical to 1 minus cos square theta. You do this and then simplify this and simplify this. That is not possible. You can't do this. When you are proving identities, while in the process of proving, you can't take this cos square to the other side or sine square to the other side. That is not allowed. Okay. The reason for that is when you take one term, you take something from one side to the other side, you are basically assuming that these are identical, right? Only then you can take that to the other side. You can't assume that because that is what you have to prove. You have to prove that this side is identical to this side. So while you're proving this, not assume that they're identical. You have to keep them separate. You can't switch terms. You can't bring one term to the other side like this. That's not allowed. Okay. So keep the two sides separate while you're proving identities. The left hand side should be separate. The right hand side should be separate. You can't take terms from one side to the other. That's not allowed. Is that okay?
Yes,
Any
sir.
problem with this? Okay, now some tips that you might find helpful when you are proving identities. We'll have a look at a couple of more examples after this. Hopefully, do we have time? Yeah. We can look at a few at least. Some tips that you should keep in mind while you're proving identities. Number one, this is very helpful, and that is keep the denominator unsimplified to see if any cancellation is possible. At a later step. What does that mean? Sometimes you'll have in the denominator something like this, sine theta into maybe 1 plus cos theta. Okay? Do not simplify this. Do not write it as sine theta plus sine theta into cos theta. But because a lot of times what would happen would be that either sine theta or 1 plus cos theta would get cancelled with something in the numerator. And if you write it like this, you might not be able to figure it out that, okay, you could actually factorize this like this and then cancel that out. You can go back as well, but it doesn't come to your mind very easily then, as in you can't figure that out very easily then if you've already simplified this. So it's much easier if you keep it in this factorized form. If you have something like this, do not simplify the denominator. Numerators you would need to simplify mostly, but denominators should be kept in factorized form. Okay, because to see if any cancellation is possible, and you have to do this a lot, that in the denominator you have some factorized form and something will get cancelled at some point. Then you will have to use identities a lot, those algebraic identities, remember, to make cancellation possible like this. You would have to use this a lot. A square minus b square, you would have to often write it as a plus b into a minus b. For instance, if you had something like this, 1 minus tan square theta somewhere, you could treat it as 1 squared minus tan theta whole squared. So it becomes a squared minus b squared. And then it could be written as 1 plus tan theta into 1 minus tan theta. So you have to do this a lot. Okay, so keep this identity in mind. It's used a lot while proving identities. A square minus b square, that can be factorized like this, a plus b into a minus b. Okay, and then sometimes you have to break the middle term as well to factorize things. So keep that in mind as well. You have to factorize stuff a lot. Okay. Then another thing that would often help you would be okay, so that we'll do when we're doing some of those examples. Then there was another point I am kind of forgetting that now. There was another thing that I was thinking of. But okay, so I think that will come in one of the practice questions later, and I'll add to it later. There's another thing that happens quite often as well, but we'll come to that when we do some practice questions. Okay, so just keep this in mind. When you are doing your working, keep the denominator unsimplified. Okay, that means in factorized form. And then be on lookout for this identity as well. You have to use this a lot to factorize terms, and then do some cancellation. All right, so that's what you need to keep in mind for proving identities. Now let's have a look at least one more example in this, so we can use these concepts that we just discussed. Now let me actually find one that maybe is slightly complicated. Just give me a minute. So those of you who've done any questions from the worksheet, if you have any proving identity questions that you found difficult, you can also let me know about those. We could perhaps discuss one of them. Otherwise, I'll just choose one myself. No questions? Okay, let's try question number, this one. Question number 27 from the worksheet. Most questions from the worksheet after this, at least all the questions from the first row that was assigned, I would expect you to have done those tomorrow. Tomorrow we'll be doing some more concepts. There are a number of small details in this topic. So we will be doing some more new things tomorrow, inshallah. Let's have a look at this for now. So we have to prove this identity on the first part. 1 over sine theta minus 1 over tan theta whole squared. That is identical to 1 minus cos theta over 1 plus cos theta. Now, which side is more complex? You can see the left-hand side has okay, I think just skip a minute. My AirPods are again disconnected. Can you hear me again?
Yes, sir.
Yes. Okay.
Yes, sir.
All right. So which side do we start from? You can see the left-hand side has different functions. The right-hand side only has cos. So it's going to be better to start from the left-hand side. The left-hand side also has a square. Expanding that square is going to be easier as compared to converting this to a perfect square, right? So we start from the left. Minus 1 over tan theta whole squared. Okay, now how do we start? How do we start with this? What should we do?
Sir,
Yeah,
can we convert 1 over tan theta into cos over sine?
into cos over sine. Yeah, so that's a very good starting point. Should we do that first, or should we take LCM first?
Sir, LCM.
Should we do LCM first? Why would you do LCM first? So we have two options, right? At this point, so we have two paths that we can follow. We can say either convert this to sine over cos first, or cos over sine in this case, or first take LCM and then do something else. How would you decide which one to do? So how many
Sir,
of you
LCM would be a longer way.
LCM would be longer? Why? What would be the problem with that? If you were to take LCM here, denominator you would get sine theta into tan theta, and in the numerator you would have tan theta minus sine theta, and then you have whole squared on top of that as well. And if you convert it to sine over cos now, it's going to make things complicated, yes. On the other hand, if you were to convert tan to sine over cos before taking LCM, let's see what happens in that case. In that case, it would become 1 over sine theta minus 1 over sine theta over cos theta. right? Now, what does this become? This cos goes to the numerator, and we end up with 1 over sine theta minus cos theta over sine theta. And now you see the denominator has become the same. Now, if the denominators are the same, it is much simpler. That's a sine theta, and in the numerator, we just have 1 minus cos theta. And this is something much simpler than what we had here. Okay. And this was another point that I actually wanted to mention here as well. When you have tan on one side, or you can say when you have tan on the side, you are starting from and no tan on the other side. It's mostly a good idea, or you can say it's mostly more efficient. It's mostly more efficient to convert tan to sine over cos right away in the very beginning. If on the other side you do not want to have a tan at the end, mostly more efficient to convert tan to sine over cos in the very beginning. Okay, that will mostly help you, and you'll find that when you do a lot of practice, you'll realize this often makes your working much more efficient. You can prove identities in much fewer steps this way. Okay, so this is something that works very well. And then there was another thing that came there as well. You can use this directly. Sometimes tan theta, remember, is this identity. Tan theta is equal to sine theta over cos theta. We know that tan square theta, therefore, is sine square theta over cos square theta. But we also understand from this that if we have 1 over tan theta, that's reciprocal of this, that can directly be written as cos theta over sine theta, right? So you can write this directly, okay? If tan is sine over cos, then 1 over tan is cos over sine, okay? Now that's not necessarily a tip as such, but just some simple algebra that you should keep in mind. If you have tan equal to sine over cos, then 1 over tan is cos over sine. You can write that directly as well. But this is important, this one, that if you have tan on one side and not on the other that you want to make it equal to, convert it in the very beginning. That will be more efficient. And that's exactly what's happening in this case as well here. If you convert tan to sine over cos in the beginning, the result that you get is much more efficient. Is that okay? What do we do now? So once we reach this step, what should we do next after this? We can kind of break the split the square between the numerator and the denominator, right? So it will become 1 minus cos theta whole squared divided by sine square theta. Now, what do you want at the end? Keep that in mind as well. You want something that is only in terms of cos at the end, right? That's what you want. So keep the end in mind. Always keep the end in mind. What do you want at the end? Often what happens is you start simplifying this and then you keep going, keep using different identities. Always keep this in mind. Okay, this is what I want at the end. This is what I want at the end. 1 minus cos theta over 1 plus cos theta. So the end result that we want is 1 minus cos theta over 1 plus cos theta. That's the result that we want. Okay, so you have to keep that in mind. Now, when you keep that in mind, do you think it's a good idea to expand this square to write it as 1 minus 2 cos theta plus cos square theta? Should you do that?
No, sir.
Expand. Why not?
Sir, it will complicate it more.
It will complicate it more. And the thing is, we already have 1 minus cos theta here. And we want 1 minus cos theta at the end here as well. It's just that the power needs to be gotten rid of somehow. Okay? But that's exactly what we want. We want 1 minus cos theta in the numerator. And we have that here already. If we can just somehow get rid of this power, we would have that. So we should not be expanding it, because if we do expand it, we would need to factorize this again. At the end, we would need to write it like this again. Okay? So it's not going to be any help. Yeah, so that's exactly why we should not be doing this, Ira. That's correct. We don't have any brackets anymore if we do this, right? It's not factorized form. We can't cancel anything out. If you have it like this, you can do cancellation. Okay? So we should not be expanding it. Okay, so we are saying numerator should not be expanded. Okay, what about the denominator? We want everything converted to something in terms of cos. So what we do is we say this can be written as 1 minus cos theta whole squared divided by sine square is 1 minus cos square theta. This is 1 minus cos square theta. Okay, so in the denominator, we've got 1 minus cos square theta now. What about this now? We wanted 1 plus cos theta, but we have 1 minus cos square theta. How do we go to that form now?
Sir, we can use identity 1 square minus cos whole square. Then we can write it as 1 minus cos theta and 1 plus cos theta.
Exactly. So that's very good. 1 minus cos square theta is the same thing as 1 squared minus cos theta squared. That's a squared minus b squared. So in the denominator, therefore, we can write 1 minus cos theta or 1 plus cos theta into 1 minus cos theta. That's a plus b into a minus b. And now what happens is 1 minus cos theta gets cancelled with 1 power of 1 minus cos theta in the numerator. In the numerator, we just have 1 left, power 1 left. And that leaves us with 1 minus cos theta divided by 1 plus cos theta. And that's exactly what we wanted. That's the same thing as the right-hand side. Okay? And that's the identity proved. Now, you could have gone in the other direction earlier. If you took LCM here, it would have become tan theta into sine theta, and the numerator would have tan theta minus sine theta, and then whole squared like this. Then you would convert tan to sine over cos at this step. You would still be able to prove it eventually, as in if you do everything correctly, you can still prove it that way as well. That is also going to work. Okay, there are always going to be multiple paths to the final answer, but that's not going to be as efficient. That will take longer. Okay, it's already pretty long for 3 marks. That will be even longer if we do it that way. Okay. So again, this comes with practice. More practice you do, you'll get better at it, more efficient at it. Any questions on this? No?
No, sir.
Let's do the second part quickly, and then we end. Then it says, hence solve this equation for theta between 0 and 360. Now, hence means you have to use the previous part somehow. This is exactly what we have proved in the first part to be the same as this. So we can write the equation like this instead. We can say this equation is the same thing as 1 minus cos theta divided by 1 plus cos theta. That equals 2 over 5. Why does that help? Because in this equation, we have two functions, sine and tan. Here we have already converted it to one function, so it will be easier to solve from this onward. Okay, otherwise we'll have to do all of what we did in the first part again if we were to do this using this form. So we write it like this first, and then we solve this equation from 0 to 360. Okay, so we need to solve this for theta between 0 degrees and 360 degrees. Okay, so let's cross multiply. We get 5 minus 5 cos theta, that equals 2 plus 2 cos theta. Take everything to one side. 3 equals 7. Not everything. Take cos terms to one side, constant to the other side. That gives you 7 cos theta equals 3. And cos theta equals 3 over 7. Find the basic angle. Cos alpha equals 3 over 7. What's the basic angle in degrees?
64.662.
64.62 degrees. And now since cos is positive in the first quadrant, and in the fourth quadrant, interval is from 0 to 360. So we take one angle here and another angle here. The solutions are therefore going to be theta equals 64.62 in the first quadrant and 360 minus, remember we measure angles like this. This is the second one, 360 minus 64.62, which is 295.4 degrees. That's the other answer that we're getting. So these are the two answers that we have. And that's our final result. And you see, the first part was 3 marks. And the second part is 4 marks. Now, if you're not able to do the first part for some reason, it does not mean that you leave the whole question. The first part is quite tricky in this case. Okay, it is quite tricky. But in an exam, if you're not able to do the first part, you should not be leaving the whole question. Skip it for that particular time instant. You can come back to it later, but do not skip the second part. The second part is so straightforward. That's easy 4 marks. You can do this without the first part as well. So mostly when they ask you to show something in the first part, if that part is complicated, the next parts are mostly much easier. And what happens is candidates often attempt the first part, they're not able to figure anything out, and they just leave the whole question, and that messes up their grade. You should not be leaving the whole question because of one difficult part. You already have the result from the first part. That's why they've given us as a prove that question or a show that question. You can use that result for the second part, and the second part is easy 4 marks. Okay. So always look at the next parts after a show or proof question. They're much easier in general. Okay. All right. So if you have any quick questions, you can let me know. Otherwise, we end this here. Please make sure to practice for tomorrow. We will be doing some more concepts tomorrow as well. Any quick questions before we end?
No, sir.
No? All right, good. I'll see you again tomorrow then. Allah Hafiz.
Allah Hafiz, sir.
Allah Hafiz.